Hey everyone, and welcome to This Explainer. Today we're taking an alchemist's dive straight into the ground beneath our feet. We walk on dirt, sand, and mud literally every single day, completely oblivious to the fact that they're hiding these invisible, microscopic superpowers. We're going to explore how the exact same ordinary ingredients, when they're subjected to the extreme forces of the earth, form microscopic structures that actually build the backbone of our modern industry. So get ready to look at a handful of dirt in a completely new way.
Okay, let's dive into this. Here's our roadmap for today. We're covering 1. The many faces of silica. 2. Heat, pressure, and transformation. 3. Zircon, the heat resistor. 4. The electric life of clay. And 5. Controlling clay with chemistry.
All right, Section 1, the many faces of silica. We're going to look at how one single chemical formula creates entirely different minerals. So to really wrap our heads around silica, we've got to understand the concept of polymorphs. A polymorph is basically a mineral that shares the exact same chemical ingredients as another, but it has a wildly different internal crystal structure. Think of it like taking a giant bucket of identical building blocks. You can use those exact same blocks to build a really tall tower or a wide, sturdy bridge. The ingredients haven't changed at all, but the final structure and its physical properties are completely different. And this brilliantly illustrates exactly what I mean. Notice the distinct geometric patterns of quartz, tridymite, and cristobalite. All three of these are simply SiO2, silicon dioxide. But look at how wildly different their internal patterns are. There's no way you'd think they were the same stuff. The exact same building blocks have arranged themselves into entirely distinct, complex architectures, all depending on the specific environmental conditions they were formed in. Now, at the heart of all these complex architectures is this tiny, totally invisible shape, the silica tetrahedron. You can see it modeled here with these wooden balls. It's literally just one silicon atom surrounded by 4 oxygen atoms. In minerals like quartz, these tiny tetrahedrons share their oxygen atoms with the adjacent tetrahedrons, linking together in this microscopic spiral. And it's this continuous geometric linking that gives quartz its famous hardness and stability. Moving right along to Section 2, heat, pressure, and transformation. This is where we talk about forcing these minerals to change their identities. Take a look at the intense temperature thresholds mapped out on this flowchart, showing how silica transitions from one polymorph to another. Now, you might be thinking, okay, so what? Why does a temperature chart matter? Well, manipulating these exact temperature thresholds is literally how we manufacture the modern world. For instance, when we cool molten silica really quickly, we get amorphous fused silica, which is just everyday drinking glass. And those tough, high-temperature transitions, they allow us to create industrial proppants, or frac sand, that's sand pumped deep underground to physically prop open rock fissures under immense pressure to recover oil and gas. We are basically using the Earth's geology against itself. So when we heat these minerals up, they transition in one of 2 ways. The first is a reconstructive transition. And man, this is violent. It requires massive amounts of energy to literally break the existing chemical bonds and reconstruct entirely new ones. It's like tearing down an entire house just to build a new one. The second way is a displacive transition. This requires very low energy because, well, you aren't actually breaking bonds, you're just distorting or bending them slightly. It happens easily and quickly, kind of like just rearranging the furniture in a room. And just to give you a real sense of the extreme energy we're talking about for those reconstructive transitions, 1,713 degrees Celsius. That is the melting point of alpha cristobalite. I mean, we are talking about volcanic conditions here. These crystalline structures are incredibly stubborn, requiring almost unimaginable heat to finally break down and turn into a liquid melt. Which brings us to Section 3, zircon, the heat resistor. The heavy-duty cousin of silica built for absolute extremes. Now, what's really interesting about this slide is the sheer scale of these numbers. If silica is our versatile shapeshifter, then zircon is the heavy-duty superhero. Look at these raw stats. That melting point, up to 2,450 degrees Celsius. That absolutely dwarfs silica. It also has a specific gravity over 4.6, meaning it is incredibly dense and heavy physically. Zircon is a nesosilicate, and it precipitates directly from silicate melts with just unbelievable resilience. And those raw stats, they translate directly to mind-blowing real-world applications. Think about it. When engineers need to cast liquid, molten metal, what do they use to build the mold? They use zircon sand. Because of its massive thermal resistance and low thermal expansion, a zircon mold can literally hold molten metal without melting itself, without cracking, and without the liquid metal penetrating its surface. It's basically the ultimate thermal shield in manufacturing.
Let's pivot to Section 4, the electric life of clay. We're uncovering the microscopic forces that make mud work.
So, we're shifting our journey now from the hard, dry, high-heat crystals of sand and zircon straight into the fluid dynamics of wet mud. Because clay actually has a surprisingly electric and chaotic microscopic life. Let me ask you a simple question. Next time you step in a puddle of mud, ask yourself, why does clay stick together? Why does it clump up on your boots, whereas wet beach sand just washes right off? Well, the secret lies in a series of invisible physical forces.
This right here is a clay micelle, which is just a fancy term for a single clay particle. The absolute best analogy for this is to imagine tiny playing cards. Clay particles are flat and thin. The large, flat faces of the playing card hold a negative electrical charge, but the thin edges of the card, they hold a positive electrical charge. So inside a clump of mud, you have millions of these tiny charged playing cards swimming in water, with their positive edges constantly interacting with their negative faces.
Section 5. Controlling clay with chemistry. The industrial tug-of-war between clumping and flowing. Now that we know clay is basically a giant soup of electrically charged playing cards, we can look at how human engineers play this massive game of chemical tug-of-war to force the clay to do exactly what we want. So the crucial point here is a process called flocculation. If you have a ceramic glaze or a slurry that is way too runny, you don't necessarily want to wait days for the water to naturally evaporate. Instead, you trigger flocculation, chemically forcing the suspended particles to attract one another and clump up into larger aggregates. Let's actually walk through the chemistries step by step. To flocculate clay, you add a flocculant, like ordinary Epsom salts, which is just magnesium sulfate. This dumps a whole bunch of positive magnesium ions into the water. These positive ions basically act like magnetic glue. They rapidly attach to the edges of the clay particles, making the edges strongly positive. Suddenly, those strongly positive edges desperately seek out the negative faces of the other particles, and boom! They stick together edge to face over and over, creating this thick structural house of cards that instantly increases the viscosity of the mud. Okay, but let's flip the script entirely. What if your clay is too thick, but you can't just add water because it would ruin your recipe? That's when you use deflocculation. This is the exact opposite chemical reaction. We use it to break up those clumps and make the whole mixture runnier and much more fluid. Let's move on and see how this builds. To deflocculate, we add something like sodium silicate to the slurry. This triggers a brilliant process called cation exchange. Basically, the sodium replaces the strong multivalent cations, like calcium or magnesium, on the edges of the clay. This severely lowers the positive charge on the edges, but crucially, it leaves the highly negative faces completely intact. Because everything is suddenly dominated by a negative charge, the particles repel each other. It's exactly like trying to push the identical negative poles of two magnets together. The clay particles physically push away from each other, allowing them to de-agglomerate and flow freely without snagging. So here is a really clear juxtaposition of these two opposing superpowers. Flocculation forces clumping, deflocculation forces repelling. And we use these two chemical levers in virtually every major industry. In wastewater treatment, we use flocculation to force gross suspended solids to clump together so they can be easily filtered out. But in ceramics, we use deflocculation to create complex glazes that flow perfectly smooth over a pot before being fired in a kiln. It's all just invisible chemical manipulation. Which brings us to the end of our journey today. Next time you're walking on a sandy beach, or you accidentally step into a wet puddle of clay, I really want you to ask yourself, what invisible structural forces, microscopic spirals, and electric charges are actively shifting right beneath your feet? The Earth isn't just dead dirt, guys. It is a dynamic, highly charged chemical playground. Thank you so much for joining me on this explainer, and keep exploring.